Welcome to the survey of the elementary principles in classical mechanics. Today we are going to discuss simple applications of the Lagrangian formulation. For holonomic systems, having applied forces derivable from ordinary or generalized potentials and workless constraints, we have constructed the Lagrangian formulation of mechanics. In this framework, the constraints have been eliminated and the equations of motion are written for scalar functions as opposed to the vector equations of Newton's formalism. When the method is applicable, we need only set up t and v in generalized coordinates, calculate L, and obtain the equations of motion. If we look at the structure of the kinetic energy, starting from its definition as 1 over 2 times a sum over particles from the mass of each particle times the square of the particle's velocity, uh, this is the square of the total derivative with respect to time of the particle's radius vector. And since this is the radius vector is now a function of generalized coordinates, we can expand it accordingly, and we obtain a structure of three terms. Let's see, the one here is called m0, and this one is going to be mj, and this one should be mjk, and together with everything else around them, they constitute the terms t0, t1, and t2. So you see that T, or the kinetic energy, is formed from three homogeneous functions of the generalized velocities. They are homogeneous in the sense that they have a multiplicative scaling behavior. If these velocities are multiplied by a factor, then the kinetic energy is also multiplied by a power of that factor across. And you see that T0 is independent of the generalized velocities, T1 is linear in them, and T2 is quadratic. Furthermore, T2 is the only non-vanishing term for scleronomous constraints. That is because both this one and this one contain this partial time derivative, which partial derivative with respect to time, which vanishes in the case of scleronomous constraints. Now the first application is that of a single particle in space, discussed first in Cartesian coordinates. So we will have the Lagrange equation in their general form. We have only the kinetic energy. There is no potential as the particle is outside the influence of any given field, but it can be under the action of some force which is contained in the generalized force here. So T is written again in the summation convention as m over 2 times the velocity squared, and then these derivatives are very simple to calculate. This one is 0 with respect to coordinates. This is the particle's linear momentum, and when you apply the time derivative here and use this identity, you simply obtain Newton's equations. So mass times acceleration is going to be equal to the force. The same example can be discussed in plane polar coordinates, where I'm writing the x and y coordinates in terms of the radius r and the angle phi, and then we can just take the derivatives with respect to time, and we construct the kinetic energy as a sum of two squares. One is the radial velocity, the other is the angular velocity. And in order to find the components of the force, it's useful to write the element of a vector, and what is here given is the vector element and cylindrical coordinates, but we can consider that the plane is fixed, so we can forget about this and just look at the first two versors, case in which we just apply the definition for each component of the force along the r or phi coordinate, and we obtain the two components respectively as the radial component of the applied force and the radius times the angular component of the force. And then we construct the Lagrange equations for each coordinate. For the radial coordinate, we obtain the equation here, which contains the radial and the centripetal acceleration and the radial component of the force. And for the angle phi, we immediately obtain what is the torque equation for the angular momentum here and the applied torque. The second example is that of Atwood's machine, which is a conservative system with holonomic scleronomos constraints, as the pulley is considered frictionless and massless. The one degree of freedom is the vertical position of one of the weights. The other position is determined by the length of the cable binding them. So we have the diagram here. I'm assuming that M1 is the heavier mass, case in which the gravitational potential is written in such a way that it has the highest value when x is equal to 0, when it reaches minimum when x is equal to L, which is the length of the cable between the weights. The kinetic energy is the simple expression here, and then we can construct the Lagrangian right away, calculate its derivatives, and construct the trivial equation of motion, which is just it's the well-known result that can be obtained through much more elementary methods. So the acceleration of the system is the difference of the masses divided by their sum and multiplying the gravitational acceleration. Notice that the force of constraint given by the tension in the cable never appears in the Lagrangian formulation, but neither can it be obtained directly through this method. And as a third example, we will consider a ring on a rotating wire in force-free space. This system exemplifies a mechanical problem featuring holonomic Riemann constraints. The wire is assumed to rotate with constant angular velocity omega. In this case, we once again write the Cartesian coordinates in terms of the polar ones, but now only the radius is a degree of freedom, as the uh, angular velocity is given by the constraint applied to the system. And as such, though the kinetic energy is once again a sum of two terms, it is not a homogeneous quadratic function of the generalized velocities, because the second term here is not the generalized velocity corresponding to a degree of freedom. It is simply induced by the constraint that is applied to the system. So if we take the derivatives with respect to r and the radial velocity, we construct the equation of motion, which looks like the equation for a simple harmonic oscillator, except the sign is flipped. And the general solution to this equation is a linear combination of hyperbolic functions, and the two constants can be determined from the initial conditions of the system. So we consider that at t equals 0, the radius is at some value r0, and the radial velocity is 0. And if we apply and solve the system of equations following from this, we obtain that r of t is just r0 times hyperbolic cosine of omega t. So the ring moves exponentially outward on the wire due to the centripetal acceleration, and the force of constraint is still not supplied. But we can determine it in the following way. Now that we know the position of the ring as a function of time, so it is written here in polar coordinates, but we can write the radial versor in Cartesian components. And once we have it expressed like this, we can just take the time derivative of the radius vector to find the velocity in Cartesian components. And knowing this, it means that we know the linear momentum. And since we also know r, we can take the cross product to determine the angular momentum, which turns out to have this expression pointed along the z-axis. Knowing the angular momentum, we can take its time derivative to calculate the torque that is being applied to the ring, which is given by the formula here. So this means that the force of constraint is perpendicular to both the radius vector and the angular momentum. And we can, knowing this and this, we can immediately calculate its magnitude as being given by the formula here. So it's essentially a hyperbolic sine with some parameters determined by the conditions of the problem, and it is perpendicular to the other two versors that define the cylindrical coordinates. So in summary, we have worked out a number of simple applications of the Lagrangian formulation, starting with the fifth particle in space described by Cartesian and plane polar coordinates. The Atwood machine was given as an example of a system subjected to scleronomous constraints. A ring sliding on a rotating wire served as an example of a system under rheonomous constraints. In part 2 of this series, we will be working out various problems and exercises as applications of the elementary principles of mechanics that we have studied until now. Until then, thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.